Right now, the farthest object humanity has ever launched is drifting through interstellar space at 38,000 miles per hour. At that speed, reaching the nearest star would take 73,000 years, so scientists proposed going faster. But when they calculated what happens to a spacecraft at 10% the speed of light, they discovered something terrifying. A single grain of dust, smaller than a human hair, strikes with the force of a bomb, and that is only one barrier. The universe did not place a single wall between us and the stars. It built a chain of them: distance, energy, radiation, time, biology, and physics itself, each one linked to the next, so that solving any single problem makes another one worse. This is the barrier the universe built. If you want to understand why the stars may stay forever out of reach, consider hitting that like and subscribe button. It helps us reach more curious minds like yourself. Now, get yourself comfortable. Let's begin. Every civilization that ever looked at the night sky asked the same question: what is out there? The Polynesians navigated thousands of miles of open ocean using nothing but stars and wave patterns. The ancient Greeks imagined celestial spheres carrying points of fire across a dome of darkness. Chinese astronomers recorded supernovae visible to the naked eye and wondered what forces could make a star explode. Aboriginal Australians read the dark spaces between the stars and built stories from the shape of absence itself. Every culture, on every continent, across every century, stared upward and felt the same pull. The stars were calling. Humanity wanted to answer. That desire never faded. It grew. It sharpened. Modern science inherited the ancient longing and added something dangerous to it: precision. We learned to measure the distances to stars. We calculated the energy required to reach them. We designed theoretical spacecraft on paper and simulated their trajectories on computers. We identified specific destinations, specific worlds, specific atmospheres that might harbour biology. And the numbers that came back from all of this precision were not merely large. They were a different kind of large, a kind of large that breaks the relationship between ambition and possibility. The dream of reaching another star is not a fantasy born from ignorance. It is a desire that grows stronger the more we understand. Astronomers have confirmed more than 5,000 exoplanets orbiting nearby stars. Some sit in habitable zones where liquid water could exist on rocky surfaces. In 2026, researchers identified 45 rocky worlds as top habitable zone targets, with especially promising systems including the 7-planet TRAPPIST-1 system, roughly 40 light-years away, and Proxima Centauri at just 4.24 light-years. The James Webb Space Telescope is analysing the atmospheres of these worlds right now, searching for chemical signatures that might indicate biology. The targets are real. The destinations exist. The question has never been whether there is somewhere worth going. The question is whether the universe will let us get there. And the answer begins with distance. Not distance as humans normally experience it. Not the kind of distance that patience and fuel can overcome. A different kind of distance entirely. A distance so extreme that it transforms every variable in the problem and makes the journey itself physically hostile to the traveller. This is where the first wall rises. Right now, the farthest human-made object in existence is a spacecraft, roughly the size of a small car, drifting through darkness beyond our solar system. Voyager 1 launched from Kennedy Space Center on September 5, 1977. Its original mission was to study Jupiter and Saturn up close. It completed that mission decades ago. Since its flyby of Saturn in November of 1980, Voyager 1 has been traveling on the same trajectory, at the same speed, heading outward into interstellar space. It crossed the boundary of the heliosphere, the protective bubble of charged particles generated by our Sun. In August of 2012, it became the first human-made object to enter interstellar space. It has been out there, alone, ever since. Now it is approaching another milestone. On November 18th, 2026, at roughly 2:16 in the morning Pacific time, Voyager 1 will become the first human-made object to reach one full light day from Earth. NASA confirmed this projection in its April 2026 Voyager status update. 1 light day means that a radio signal traveling at the speed of light, the fastest anything can move in this universe, will take 24 hours to reach the spacecraft. Send a command in the morning. Wait all day. Wait all night. The response arrives the following morning. A full day for light itself to bridge the gap. Voyager 1 travels at approximately 17 kilometers per second. That is roughly 38,000 miles per hour, or about 61,000 kilometers per hour. At that speed, you could circle the Earth in roughly 40 minutes. You could reach the Moon in roughly 6 hours. You could cross the distance from Earth to Mars at closest approach in fewer than 60 days. Voyager 1 is fast by any standard human beings have ever applied to a moving object, and it has been flying for nearly 50 years. In that time, it has covered roughly 1 light day. 1. That number needs to settle in your mind for a moment, because the nearest star to our solar system, Proxima Centauri, is not 1 light day away. It is 4.24 light years away. A light year contains 365.25 light days. Proxima Centauri sits approximately 1,550 light days from Earth. Voyager 1, after half a century of uninterrupted flight, has crossed less than 1/1500th of the distance to the closest star. If Voyager 1 were aimed directly at Proxima Centauri, which it is not, it would arrive in approximately 73,000 years. 73,000 years ago, modern humans shared the planet with Neanderthals. The entire history of agriculture, writing, cities, mathematics, empires, industry, and space exploration fits comfortably inside the last 10,000 years. Voyager would need 7 times that span to reach 1 star, the nearest one. As of mid-2026, Voyager 1 is over 166 astronomical units from Earth. An astronomical unit is the average distance from Earth to the Sun, roughly 93 million miles. Voyager has travelled more than 15.8 billion miles. It sounds extraordinary. It is extraordinary. And it is almost nothing compared to the interstellar gulf. Proxima Centauri lies roughly 268,000 astronomical units away. Voyager 1, after the longest continuous journey in human history, has covered approximately 6/100ths of 1% of that distance. And here is a detail that makes the distance even more disorienting. Voyager 1 has not actually left home. It crossed the heliosphere in 2012, passing beyond the bubble of charged particles streaming outward from the Sun. That milestone was real and significant. Voyager entered the space between stars in the sense that it now flies through interstellar plasma rather than solar wind. But the Sun's gravitational territory extends far beyond the heliosphere. Our star holds a vast shell of icy bodies in its gravitational grip, a structure called the Oort cloud. This enormous reservoir of comets and frozen debris is believed to begin at roughly 2,000 astronomical units from the Sun and stretch outward to as far as 100,000 astronomical units, approximately 1.5 light years. It forms a diffuse spherical shell surrounding the entire solar system, marking the true gravitational boundary of our star's domain. Voyager 1, at 166 astronomical units, has not reached the inner edge of this shell. It will not enter the Oort cloud proper for centuries. It will not clear the outer boundary for roughly 30,000 years. By the time Voyager finally exits the Sun's gravitational sphere of influence completely, the civilization that built it will need to have survived longer than the entire span from the first cave paintings to the present day. And at that point, after 30,000 years of flight, Voyager will still not even be halfway to Proxima Centauri. The heliosphere was never the border. It was a curtain inside a much larger room. Voyager 1 has pushed through the curtain. The door is 30,000 years ahead. The nearest neighbour is 40,000 years beyond that. Our fastest, most distant traveller has not even finished the act of leaving home. This is where human intuition fails for the first time, but not the last. Numbers this large resist comprehension. The brain evolved to process distances a body can walk, territories a hunter can cross, horizons an eye can scan. Nothing in human evolutionary history prepared the mind to hold interstellar distances as real quantities rather than abstract symbols on a page. So let me try to make it tangible. Imagine shrinking the entire solar system so that the Sun becomes a basketball sitting on a sidewalk in New York City. At this scale, Earth would be a small grain of sand orbiting roughly 26 meters away, about 85 feet. Jupiter would be a marble, about 135 meters from the basketball, a block and a half down the street. Neptune, the outermost major planet, would be a small pea sitting roughly 800 meters away, about half a mile from the Sun. The entire known solar system, from the Sun out past Neptune's orbit, fits within a modest walk through a single borough. Voyager 1, after nearly 50 years of flight, would have travelled roughly 40 blocks beyond Neptune at this scale, about 2 miles past the edge of the solar system. It would still be in Manhattan. Now find Proxima Centauri. At this same scale, the nearest star would be another basketball sitting on a sidewalk in Honolulu, Hawaii, over 4,000 miles from New York. Between those two basketballs stretches nothing. No gas stations, no landmarks, no waypoints, no emergency shelters. Just 4,000 miles of bare table with a few grains of sand clustered near one basketball and nothing at all until you reach the other. That is the interstellar void. That is what separates us from the nearest star. This model is not an exaggeration. If anything, it understates the emptiness. The interstellar medium, the material that fills the space between stars, averages roughly 1 hydrogen atom per cubic centimetre. Compare that to the air you are breathing right now, which contains approximately 25 billion molecules per cubic centimetre. Interstellar space is not merely empty, it is a void so thorough that it challenges the meaning of the word emptiness itself. Laboratories on Earth cannot produce a vacuum this clean. The best vacuum chambers ever built contain millions of molecules per cubic centimetre. The space between stars puts them to shame. And here is why this matters beyond sheer scale. Interplanetary travel and interstellar travel are not different points on the same spectrum. They are fundamentally different categories of problem. The distinction is not one of degree, it is one of kind. Consider what humanity has achieved within the solar system. We have landed rovers on Mars and driven them across its surface for years. We have dropped a probe onto Titan, a moon of Saturn, and photographed its methane lakes. We have sent spacecraft past every major planet, including a flyby of Pluto at the edge of the solar system. We have parked an observatory at the second Lagrange point, 1.5 million kilometers from Earth. These are genuine triumphs of engineering and determination, but they all share one critical feature. They were accomplished within a region where distances are measured in light minutes or light hours. A signal from Earth to Mars takes between 4 and 24 minutes depending on orbital positions. That delay is manageable. Mission controllers can send a command and receive confirmation within an hour. Software can be uploaded, errors can be corrected, trajectories can be adjusted in real time. The spacecraft remains within communicative reach of its builders. Problems can be diagnosed and solved from the ground. This is what makes interplanetary exploration possible. Not just propulsion and navigation, but the ability to maintain a functioning relationship between the machine and the people who built it. The distance to Proxima Centauri is roughly 700,000 times the distance from Earth to Mars at closest approach. That is not a percentage increase. It is a multiplication by a factor approaching 1 million. The jump from interplanetary to interstellar is a change of nearly 6 orders of magnitude. It is the difference between walking across a room and walking across a continent. The tools that work at one scale do not function at the other. The strategies that conquered solar system distances do not transfer. When a Mars rover develops a software glitch, engineers at the Jet Propulsion Laboratory can diagnose the issue and upload a fix within a day. When a spacecraft 4 light-years away develops the same glitch, the earliest Earth could learn about the problem is 4 years after it occurs. The earliest a fix could arrive is 8 years after the malfunction. By then, the mission may be over. The crew may be dead. The systems may have cascaded into failure modes that no upload can reverse. Communication delay is only one consequence of the distance. Resupply becomes physically impossible. There is no cargo vessel fast enough to catch an interstellar spacecraft. Every gram of food, every litre of water, every replacement component, every medication must be carried from launch or manufactured aboard. Rescue becomes a meaningless concept. If something goes catastrophically wrong 2 light-years from Earth, no one is coming. The crew is alone with whatever they brought and whatever they can build. To appreciate how far current technology sits from closing this gap, consider the fastest spacecraft ever built. The Parker Solar Probe, launched by NASA in 2018, holds the all-time speed record for a human-made object relative to the Sun. During its closest approaches to the solar surface, it reaches speeds exceeding 190 kilometers per second, roughly 430,000 miles per hour. That is fast enough to travel from New York to Los Angeles in about 20 seconds. It is genuinely, startlingly fast. Even at the Parker Solar Probe's peak velocity, a journey to Proxima Centauri would take approximately 6,700 years, longer than the entire span from the construction of the Great Pyramid to this moment. The fastest thing humanity has ever built, travelling at its absolute maximum speed, would still need nearly 7 millennia to reach one star, and the Parker Solar Probe only hits that speed during brief gravitational slingshots around the Sun. It cannot sustain such velocity. No existing spacecraft can. Voyager 1's steady cruise of 17 kilometers per second is far more representative of what current propulsion can maintain over long durations. New Horizons, which flew past Pluto in 2015, cruises at roughly 14 kilometers per second. Pioneer 10 and Pioneer 11, launched in the 1970s, drift outward at roughly 12 and 11 kilometers per second respectively. These are our fastest long-distance travelers. None of them were designed for interstellar missions. They were built for planetary encounters and simply kept going because no one could stop them and nothing stood in their way. None will reach the neighborhood of another star for tens of thousands of years. The gap between what humanity can build today and what interstellar travel demands is not a gap that incremental improvement will close. Chemical rockets, the workhorses of the space age, produce exhaust velocities of 3 to 5 kilometers per second. The most advanced ion engines tested in space achieve 30 to 50 kilometers per second. To reach even 1% of the speed of light, roughly 3,000 kilometers per second, would require propulsion technology that does not exist outside of theoretical papers and speculative engineering conferences. 1% of the speed of light. That sounds ambitious. It would be the fastest any human-made object has ever traveled by a factor of roughly 200. A genuine revolution in propulsion. And at 1% the speed of light, Proxima Centauri is still over 420 years away. This is where the nature of the problem reveals itself. Interstellar distance does not just make the journey longer, it transforms what the journey is. Within a solar system, spaceflight is fundamentally an engineering challenge. Build a reliable rocket, calculate the trajectory, carry enough fuel, communicate with the ground. The physics is well understood. The distances are large but manageable. The risks are containable because the timescales allow mistakes to be corrected, and the proximity allows help to arrive. Interstellar distance changes all of that. When the journey takes centuries, the spacecraft must outlast every human institution that has ever existed. When communication takes years, mission control ceases to function as a concept. When resupply is impossible, every system must either work perfectly for the entire voyage or be repairable using only materials aboard the ship. When rescue cannot come, every failure mode becomes potentially terminal. The distance does not create a bigger version of the same problem. It generates entirely new categories of problem that have no equivalent at shorter ranges. Biology becomes a barrier because human bodies do not live for centuries. Mechanics becomes a barrier because machines do not last for centuries. Sociology becomes a barrier because civilizations do not hold together for centuries in isolation. Psychology becomes a barrier because human minds do not endure total confinement for decades, let alone for generations. Each of these new barriers demands its own solution, and each solution carries its own weight, its own complexity, its own failure modes. The distance between stars is the first wall, but it earns that title not because it is the tallest. It earns it because it forces every other wall into existence. And here is where the chain begins to take shape. Interstellar distance presents every potential traveller with a forced choice. Both options look reasonable from a distance. Both collapse on closer inspection. Option 1. Travel slowly. Accept that the journey will take centuries or millennia. Build a vessel large enough to sustain a human population for the entire duration. Let generations be born, live, and die aboard the ship, so that distant descendants eventually arrive at another star. This is the generation ship, the idea that patience can substitute for speed. It sounds almost wise. In practice, it requires solving every problem that extended time creates. Radiation exposure, accumulating over centuries. Closed ecosystems recycling air, water and food without failure for longer than any civilization has maintained a single building. Mechanical systems running without external repair or resupply for durations that exceed the operational life of every machine ever constructed. Social structures holding together in permanent isolation without fragmenting, rebelling, or forgetting why the journey began. Option 2. Travel fast. Accelerate to a significant fraction of the speed of light so that the journey shrinks from millennia to decades or even years. This eliminates the biological and mechanical timescale problems almost entirely, but speed introduces its own cascade of physical hazards that are every bit as lethal as the problems it solves. Energy requirements explode as velocity increases. The interstellar medium, harmless at low speeds, becomes a barrage of high-energy projectiles. Hydrogen atoms that drift invisibly through the void at rest strike the spacecraft like cosmic rays when the ship moves fast enough. Acceleration and deceleration forces stress every structure and every body aboard, and the speed of light imposes a hard ceiling that no technology, no matter how advanced, can breach. Slow travel fails because time destroys everything human. Fast travel fails because speed turns empty space into a weapon. The distance between stars forces this dilemma, and the dilemma has no clean resolution. This is not a failure of imagination. It is a consequence of physics. The universe is structured so that the distances between stars are large enough to make every crossing strategy encounter secondary barriers that arise directly from the strategy itself. Go slow and time becomes the enemy. Go fast and energy, dust and radiation become the enemy. The first wall does not merely block the path. It splits the path into two corridors, and both corridors are mined. There is something almost personal about this barrier. Humans evolved to cross distances. Migration is written into our biology. We walked out of Africa and populated every continent on Earth. We built ships and crossed oceans that seemed limitless. We launched ourselves off the surface of our own planet and set foot on the moon. Every previous barrier of distance eventually yielded to courage, ingenuity, and time. The interstellar gulf is different. It is not simply a larger ocean. It is a distance so vast that it changes the rules of crossing. Consider this. The Roman Empire lasted roughly 500 years from the reign of Augustus to the fall of its western half. A journey to Proxima Centauri at 1% the speed of light would take 420 years. Even if humanity built a spacecraft capable of that speed tomorrow, the civilization that launched it might cease to exist before the ship arrived. The travelers would be descendants of a vanished culture, carrying a mission designed by a society that crumbled centuries before anyone aboard was born. Distance is the first barrier, and it is the one that makes every other barrier inevitable. It forces the choice between slow and fast. It eliminates rescue and resupply. It severs communication. It demands that machines outlast empires. It requires human bodies to endure what evolution never prepared them for. But distance alone is not what makes interstellar travel physically impossible for human beings. If it were merely a matter of crossing a large gap, patience and determination might eventually find a way. The true horror is what happens when you actually try to cross it. What the slow path does to ships and to the people inside them. What the fast path does to atoms and to dust and to energy budgets. Distance opens the door to a chain of barriers, each one linked to the next, each one worse than the last. The slow path beckons first. Centuries of travel through the void, a ship that must become a world, and a world that must somehow hold together long enough to reach another star. What waits along that path will make the distance itself feel almost gentle by comparison. The logic seems almost elegant at first. If the problem is distance, and if speed is limited, then perhaps the answer is patience. Build a vessel large enough to carry a community. Stock it with everything a small civilization might need. Launch it toward the nearest star at whatever speed your engines can manage, and accept that the journey will take centuries. Let the passengers live their lives aboard the ship. Let their children carry the mission forward. Let grandchildren and great-grandchildren inherit the purpose until, someday, a generation that never saw Earth steps onto the surface of another world. This is the generation ship. It is the most frequently proposed solution to the interstellar distance problem, and it has captivated thinkers for nearly a century. Konstantin Tsiolkovsky described the concept in 1928, calling it a kind of Noah's Ark equipped with engines and designed for journeys lasting thousands of years. Robert Heinlein explored it in fiction. Arthur C. Clarke refined it. Entire design studies have been conducted. Project Hyperion, run by the Initiative for Interstellar Studies, produced detailed engineering proposals for multi-generation crewed vessels. The idea keeps coming back because it appears to sidestep the most obvious physical barriers. You do not need to travel at relativistic speeds. You do not need exotic propulsion. You do not need to break any law of physics. You just need a ship that lasts and a population that endures. But when you examine what lasting and enduring actually require across interstellar timescales, the generation ship does not sidestep the barriers at all. It trades the barriers of speed for the barriers of time. And time, given enough of it, destroys everything human beings have ever built. Start with what slow actually means in interstellar terms. Even ambitious propulsion concepts that do not yet exist cannot make slow travel fast. A nuclear pulse engine, the most powerful propulsion system ever seriously studied, was the basis of Project Orion in the 1950s and 60s. It proposed detonating nuclear bombs behind a massive pusher plate to accelerate a spacecraft. Theoretical performance estimates suggested speeds of 3 to 5%. The speed of light might be achievable with large enough vehicles. At 5% of light speed, the trip to Proxima Centauri takes roughly 85 years. That is within a single human lifetime, though barely, and only if everything goes perfectly. Few serious proposals achieve even this. More realistic nuclear thermal or nuclear electric systems, the kind NASA is currently developing for Mars missions, max out at speeds orders of magnitude below 1% of light speed. At those velocities, Proxima Centauri is thousands of years away. The gap between current propulsion and even 1% of light speed is enormous, and the gap between 1% and 5% is nearly as large. For any technology plausibly available in the coming century, interstellar transit times fall somewhere between several centuries and several tens of thousands of years. That means the generation ship does not need to work for a decade. It does not need to work for a century. It needs to work for longer than most civilizations on Earth have lasted. And it needs to work perfectly, in total isolation, with no external help, in the most hostile environment human beings have ever encountered. The first thing that kills the crew is invisible. Beyond the protective cocoon of Earth's magnetic field and atmosphere, space is saturated with radiation. Two sources dominate. Solar particle events produce intense bursts of protons during solar flares and coronal mass ejections. These are dangerous but intermittent, and a spacecraft within a solar system can be designed to shelter its crew during events that last hours or days. The second source is far worse for long-duration travel. Galactic cosmic rays are high-energy particles, mostly protons but including heavier nuclei like iron, that originate from sources outside the solar system. Supernova remnants, neutron stars, black hole environments. These particles travel at nearly the speed of light and carry enormous energy. A single galactic cosmic ray iron nucleus can pack more kinetic energy than a professionally pitched baseball compressed into a particle smaller than an atom. Earth's magnetic field deflects most galactic cosmic rays. Its atmosphere absorbs much of what remains. Humans on the surface receive a background radiation dose of roughly 2 to 3 millisieverts per year from cosmic sources. Astronauts aboard the International Space Station, which orbits within Earth's magnetosphere, but at reduced shielding, receive roughly 150 to 200 millisieverts per year. Beyond the magnetosphere, in interstellar space, the unshielded dose from galactic cosmic rays alone climbs to roughly 600 millisieverts per year or higher, depending on solar cycle conditions and local interstellar environment. 600 millisieverts per year means that within 5 to 10 years of unshielded exposure, every person aboard a generation ship would exceed the lifetime radiation dose limits NASA currently sets for astronauts. Cancer rates would rise dramatically. Cardiovascular disease would accelerate. Research from the NASA Space Radiation Laboratory at Brookhaven, where mice are exposed to simulated galactic cosmic ray fields, has demonstrated persistent damage to brain structure and cognitive function. Hippocampal neurogenesis, the the process by which the brain forms new neurons critical for learning and memory, declines significantly after exposure to heavy ion radiation, at doses comparable to a multi-year deep space mission. The damage is not temporary. It persists for the life of the organism. Shielding can reduce the dose, but the physics of galactic cosmic ray interaction makes conventional shielding counterproductive beyond a certain thickness. When a high-energy heavy nucleus strikes a metal hull, it does not simply stop. It fragments, producing a shower of secondary particles, neutrons, protons, and lighter nuclei that can be more biologically damaging than the original particle. This is called spallation, and it means that adding more aluminum or steel to a ship's hull can actually increase the radiation dose to the crew, rather than decrease it. Effective shielding requires hydrogen-rich materials, water, polyethylene, or dedicated liquid hydrogen tanks, layered thick enough to slow and absorb both primary particles and secondary showers. The mass penalty is staggering. Estimates for adequate galactic cosmic ray shielding on a crewed interstellar vessel range from several meters of water-equivalent material surrounding the entire habitable volume. For a ship large enough to house hundreds of people, this means thousands or tens of thousands of additional tons of shielding mass, all of which must be accelerated to cruising speed, alongside everything else the ship carries. Every kilogram of shielding is a kilogram that could have been food, fuel, or equipment. Radiation protection does not come free. It competes directly with every other survival system aboard. And even with shielding, the dose is reduced, not eliminated. Over centuries of travel, cumulative exposure accumulates generation after generation. Genetic damage passes to offspring. Mutations accrue in the population's gene pool. A ship that launches with a healthy crew arrives with a population carrying centuries of radiation-induced genetic burden. No ground-based experiment has ever modeled what this looks like across 10 or 20 human generations because no experiment has ever needed to. The second biological crisis is genetic diversity. A generation ship cannot carry millions of people. Propulsion limits, life support capacity, and structural constraints restrict the founding population to hundreds, or at most a few thousand individuals. Population genetics studies suggest that a minimum viable population for long-term survival without unacceptable inbreeding sits somewhere between 500 and 5,000 people, depending on assumptions about reproductive management and genetic screening. Below this threshold, genetic diversity erodes with each generation. Recessive deleterious mutations become more likely to pair. Inbreeding depression manifests as reduced fertility, increased susceptibility to disease, and developmental abnormalities. Managing genetics across centuries of travel requires active intervention. Reproductive pairing must be guided or constrained to maximize outbreeding. Stored genetic material, sperm banks, egg banks, perhaps frozen embryos, must remain viable for the entire journey. Cryopreservation technology works on timescales of decades, not centuries. No biological sample has ever been preserved in a functional state for 300 years, and any system of managed reproduction raises ethical questions so profound that no human society has ever attempted to implement one at this scale. There is a third biological crisis that receives less attention than radiation or genetics, but may be equally destructive over interstellar timescales. The human body was not designed for weightlessness. It was sculpted by 4 billion years of evolution under 1 g of gravitational pull, and when that pull disappears, the body begins to dismantle itself. Data from the International Space Station, where astronauts routinely spend 6 months to a year in microgravity, reveals a consistent pattern of deterioration. Bone density decreases at a rate of roughly 1 to 2% per month in load-bearing bones like the hip and spine. Muscles atrophy, particularly in the legs and lower back, losing mass and strength despite daily exercise regimens of 2 hours or more. The cardiovascular system, no longer fighting gravity to pump blood upward, weakens and remodels. The heart itself changes shape, becoming more spherical. Fluid that gravity normally pulls into the lower body redistributes toward the head, increasing intracranial pressure. This pressure buildup affects the optic nerve and deforms the eyeball. NASA has classified this condition, known as spaceflight-associated neuroocular syndrome, as one of the top health risks for long-duration missions. Some astronauts return from year-long stays with permanent changes to their vision. On the International Space Station, These problems are manageable because astronauts return to Earth within months. Gravity reverses the bone loss over time. Muscles rebuild. Vision partially recovers. But a generation ship offers no return to gravity. The crew lives in microgravity or reduced gravity for their entire lives. Their children are born into it. Their grandchildren grow up in it. Over generations, the cumulative skeletal and muscular deterioration would produce a population physically incapable of functioning on a planetary surface. The people who arrive at the destination, assuming they survive everything else, may not be able to stand up under the gravity of the world they came to inhabit. The obvious solution is artificial gravity through rotation. Spin the ship or a section of it fast enough, and the centrifugal effect pushes occupants outward against the hull, mimicking gravitational pull. This is real physics, and it works. But the engineering requirements are formidable. The human vestibular system is sensitive to rotational motion. If the habitat rotates too quickly, occupants experience severe motion sickness and disorientation from Coriolis effects, the apparent forces that deflect moving objects inside a rotating frame. The smaller the radius of rotation, the faster the spin rate needed to produce 1g, and the worse the Coriolis effects become. Studies on human tolerance suggest that rotation rates above roughly 2 revolutions per minute produce unacceptable discomfort for most people. To stay below this threshold while generating 1g of centrifugal acceleration, the habitat must have a radius of at least 225 meters. That means a spinning structure roughly 450 meters across. Building a rotating habitat of that scale, strong enough to withstand the structural stresses of continuous rotation for centuries, adds thousands of tons of mass to the ship. The bearings or joints connecting the rotating section to the non-rotating propulsion system must function without maintenance for the entire voyage. Rotating seals that allow the transfer of power, atmosphere, and materials between spinning and stationary sections must operate continuously for longer than any rotating seal in human engineering has ever lasted. Every kilogram of rotating structure is a kilogram added to the total mass that must be accelerated to cruising speed, feeding directly back into the propulsion and fuel constraints that already strain the design to its limits. And partial gravity introduces its own unknowns. What happens to human development in 1/3 g or 1/2 g over multiple generations? No one knows. No experiment has ever tested multi-generational mammalian reproduction at reduced gravity. It is possible that embryonic development requires a full G to proceed normally. It is possible that bone formation in children fails below some gravitational threshold that has never been measured because there has never been a reason to measure it. The generation ship must choose a gravity level and commit to it for the entire voyage, with no ability to correct the decision if the chosen level turns out to damage the biology of every person born aboard. Gravity is invisible. It does not explode or irradiate or corrode, but its absence reshapes the human body over months and would reshape the human species over centuries. The generation ship must either solve this problem or accept that the population arriving at the destination will be biologically different from the population that launched, changed by the absence of a force so constant on Earth that no human being in history has ever had to think about it. But even if radiation could be fully shielded, genetics carefully managed, and gravity somehow addressed, the ship must sustain its passengers biologically for the entire journey. That means food, water, and air, recycled without loss, for centuries. No closed ecological life support system has ever operated successfully for more than a few years. Biosphere 2, built in Arizona in the late 1980s, was the most ambitious attempt. A sealed enclosure of roughly 3.14 acres, it housed 8 people and was designed to recycle all air, water, and food indefinitely, using a miniature ecosystem of plants, animals, insects, and microbes. It failed within the first 2 years. Oxygen levels dropped dangerously as carbon dioxide accumulated beyond what the plants could process. Concrete inside the structure absorbed oxygen through chemical reactions no one had anticipated. Insect populations crashed. Pollination failed. Crop yields plummeted. The crew experienced chronic hunger and interpersonal conflict. Biosphere 2 had to be opened and resupplied. The Soviet BIOS 3 experiment in the 1970s achieved longer closure durations, up to 180 days, with a simpler system based on algae cultivation and wheat farming in a much smaller habitat. It provided some lessons about gas exchange and waste recycling, but never approached the complexity or duration required for interstellar travel. The European Space Agency's Melissa project has been studying closed-loop life support for decades and has made progress on individual subsystems, waste processing, air revitalization, water recovery, but has not yet demonstrated a fully closed system capable of sustaining even a small crew indefinitely. The International Space Station does not even attempt closure. It receives regular resupply missions carrying food, water, oxygen, spare parts, and equipment. Its life support systems recycle some water and scrub carbon dioxide from the air, but it depends utterly on Earth for survival. Without resupply, the station would become uninhabitable within months. A generation ship must achieve what no habitat in human history has achieved: total closure, complete recycling, zero external input for 300 years, or 3,000 years, or 30,000 years. Every atom of carbon, every molecule of water, every trace element required for biology must cycle endlessly without accumulating in the wrong reservoir or leaking into unusable forms. In Earth's biosphere, these cycles are maintained by a planet-sized system with oceans, forests, atmospheric circulation, tectonic activity, and billions of years of evolutionary tuning. Replicating this inside a metal hull is not an engineering challenge in the conventional sense. It is an attempt to build a miniature planet from scratch and keep it running longer than any human structure has ever survived. Which brings us to the next wall. Machines break, everything breaks, and nothing humans have ever built keeps running for centuries without repair. Voyager 1 is the longest operating spacecraft in history. Launched in 1977, it has been functioning in some capacity for nearly 50 years. But functioning is a generous description. Most of its scientific instruments have been shut down to conserve the dwindling power from its radioisotope thermoelectric generators. Those generators produce electricity from the decay of plutonium-238, and they lose roughly 4 watts of output per year as the plutonium decays. By 2026, Voyager 1's power budget has dropped to roughly 225 watts, barely enough to run a few light bulbs. NASA engineers have systematically deactivated heaters, instruments, and subsystems to keep the most essential equipment alive. Within the next few years, there will not be enough power to operate anything at all. Voyager 1 will go silent, not because it was destroyed, but because its power source decayed on schedule. A generation ship faces this same problem multiplied by every system aboard. Reactors degrade, bearings wear, seals leak, electronic components accumulate radiation damage and fail. Software develops bugs that compound over time. Structural materials fatigue under cyclic stress. Moving parts, pumps, fans, valves, compressors, centrifuge bearings, all have finite operational lifetimes measured in years or decades, not centuries. A study published on Centauri Dreams in 2025 examined whether an interstellar generation ship could maintain its population over a 250-year voyage. The author noted that apart from simple technologies, no Industrial Revolution era or later technology that continues to work has operated without the repair of parts. Our largely solid-state space probes, now over 45 years old, would not work reliably for 250 years, even if their failing power sources were replaced. Mechanical moving parts fail even faster. On Earth, we maintain complex machines through supply chains. A jet engine lasts tens of thousands of flight hours because it is regularly inspected, and worn turbine blades are replaced with new ones, manufactured in factories that source materials from mines that extract ore from the ground. Every link in that chain depends on an industrial civilization with millions of workers, global logistics, and raw material extraction. A generation ship has none of this. It carries whatever it launched with. If a critical pump fails in year 200 and no replacement exists aboard, the system it served stops working. If that system was part of the life support loop, people start dying. Theoretically, a ship could carry workshops, fabrication equipment, and raw material stockpiles sufficient to manufacture replacement parts on board. But this adds enormous mass, complexity, and the need for skilled technicians across every generation. Training programs must function continuously for centuries. knowledge must transfer perfectly from one generation to the next. A single generation that fails to train enough machinists, enough chemists, enough electrical engineers, risks a cascading loss of maintenance capability from which the ship cannot recover. This is where the mechanical barrier meets the civilizational barrier, because machines require people to maintain them, and people require functioning social structures to maintain specialized knowledge. Long-duration isolation studies on Earth provide grim precedents. The Mars 500 experiment, conducted in Moscow between 2010 and 2011, confined 6 volunteers in a sealed habitat for 520 days to simulate a Mars mission. The crew experienced sleep disruption, depression, social withdrawal, and interpersonal conflict. One crew member became so sedentary and disengaged that researchers worried about his physical and psychological health. And these were carefully selected, highly motivated volunteers who knew the experiment would end, who could communicate with the outside world, and who were confined for fewer than 2 years. A generation ship confines its population not for months or years but for lifetimes. Children born aboard the ship never chose the mission. They inherit it. They grow up inside a metal hull with no horizon, no weather, no natural landscape, no possibility of leaving. They know from the moment they are old enough to understand that they will live and die inside this container, and that the destination their great-great-grandparents chose will not be reached in their lifetimes. What does this do to motivation? What does it do to purpose? What does it do to the willingness to maintain complex technical systems that serve a goal you will never personally benefit from? Historical precedents are not encouraging. Isolated communities on Earth, even those with access to outside resources, frequently experience social fragmentation over much shorter timescales. Island populations develop unique cultural practices within a few generations. Linguistic drift creates mutually unintelligible dialects within centuries. Religious movements transform societies within decades. Political structures rise and fall. Knowledge is lost and reinvented. The fragility of specialized knowledge across generations is better documented than most people realize, and the examples are sobering. After the fall of the Western Roman Empire in the 5th century, Europe lost the ability to produce concrete. Roman concrete, a material so durable that structures built with it still stand 2,000 years later, required specific knowledge of volcanic ash ratios, mixing techniques, and curing processes. That knowledge vanished within a few generations. It was not rediscovered until the 18th century. Over 1,000 years later, the Romans also built aqueduct systems of extraordinary precision, engineered to maintain a steady gradient across miles of terrain. After the empire collapsed, the maintenance knowledge disappeared. The aqueducts fell into disrepair. Cities that had enjoyed running water for centuries reverted to wells and rain collection. The technology was visible. The structures were standing. The knowledge to keep them functioning was gone. The Polynesian navigation traditions offer an even more pointed example. For thousands of years, Pacific Islanders crossed vast stretches of open ocean using a system of wayfinding based on star positions, wave patterns, bird behavior, and subtle changes in watercolor and temperature. This knowledge was transmitted orally from master navigators to apprentices across dozens of generations. It worked flawlessly. Then European contact disrupted the transmission chain. Within 3 generations, much of the knowledge was nearly lost. Only a handful of master navigators in Micronesia and Polynesia preserved fragments of the tradition into the 20th century. A knowledge system that had survived thousands of years of transmission collapsed in fewer than 100 years when the social structures supporting it were disrupted. In the modern era, the challenge of transmitting critical knowledge across even modest timescales has proven surprisingly difficult. The United States Department of Energy has spent decades attempting to design warning markers for nuclear waste repositories that must remain comprehensible for 10,000 years. The problem is not engineering. The markers can be made durable. The problem is language. No human language has survived unchanged for 10,000 years. No symbol system has maintained consistent meaning across that span. The department convened panels of linguists, anthropologists, semioticians, and artists, and the consensus was humbling. There is no known method for guaranteeing that a message created today will be understood by humans 10,000 years from now. Proposals ranged from hostile architecture designed to convey danger through emotional response rather than language, to breeding genetically modified cats that change color in the presence of radiation. None were adopted. The problem remains unsolved. A generation ship needs its crew to transmit not a simple warning, but an entire technical civilization across centuries of isolation. Metallurgy, chemistry, medicine, electrical engineering, software development, agricultural science, mechanical repair, dozens of specialized disciplines, each requiring years of training, each depending on the others. If any single generation fails to produce enough trained specialists in any single critical field, the ship loses the ability to maintain the systems that depend on that field. And unlike Earth, where a lost technology can sometimes be rediscovered through experimentation or contact with other cultures, a generation ship has no external source of knowledge. What is lost stays lost. The library is finite, the teachers are mortal, and the students may not want to learn what their parents insist they must. Aboard a generation ship, these processes unfold in a closed system where the consequences of social failure are not cultural decline but physical death. If a generation rejects the mission, there is no external authority to reimpose it. If technical knowledge decays because a generation prioritizes other concerns, the ship's systems degrade without anyone capable of repairing them. If internal conflict splits the population into factions, the losers cannot leave. They are trapped inside the same hull as their opponents, sharing the same air and water. The generation ship requires something no human society has ever demonstrated: perfect transmission of purpose, knowledge, and social cohesion across dozens of generations in total isolation. Every historical attempt at multi-generational institutional continuity has relied on external pressures, trade relationships, competing societies, environmental challenges, immigration, cultural exchange. To renew itself, a generation ship has none of these renewal mechanisms. It must maintain itself purely from internal resources, social and psychological as well as material, for longer than most earthly civilizations have managed to persist even with the entire planet to draw upon. And all of this assumes the ship launches without error, that the initial design contains no fatal flaw, that no unforeseen physical phenomenon in interstellar space damages the vessel in ways the designers did not anticipate, that no asteroid or rogue body sits undetected along a trajectory plotted centuries in advance. These are serious concerns, but there is a deeper one that is almost never discussed. What if the destination is wrong? The generation ship concept depends on knowing, before launch, that a habitable world exists at the end of the journey. This knowledge comes from telescopes. Astronomers observe a distant star, detect a planet orbiting in the habitable zone, analyze the spectrum of light filtering through its atmosphere, and infer conditions that might support human life. These observations are real and increasingly precise. The James Webb Space Telescope can identify the chemical composition of exoplanet atmospheres from light years away: carbon dioxide, water vapor, methane, oxygen, the signatures of a world that might be habitable. But inference is not confirmation. A spectrum tells you which molecules float in an atmosphere. It does not tell you whether the surface is solid or molten. It does not reveal the acidity of the oceans, the toxicity of the soil, or the presence of microbiology that might be lethal to Earth-based organisms. It does not describe the radiation environment on the surface, the frequency of volcanic eruptions, the stability of the climate over centuries, or whether the tidal forces from the host star have locked the planet's rotation so that one side bakes in permanent daylight while the other freezes in eternal darkness. Many of the most promising habitable zone exoplanets orbit red dwarf stars, which are prone to violent flares that could strip a planet's atmosphere entirely. The telescopic data says a planet might be habitable. It cannot say a planet is habitable. That determination requires being there. A generation ship cannot hedge this bet. It carries no fuel for a second destination. It cannot turn around. The trajectory is plotted centuries in advance toward a single star system, and the passengers are committed to that trajectory from the moment of launch. If the planet turns out to be uninhabitable, the mission does not fail gracefully. It fails absolutely. Centuries of survival, of radiation endured, of machines maintained, of generations born and buried in transit, end not in triumph but in extinction at the finish line. The crew arrives at a world that cannot sustain them and possesses no means of going anywhere else. This risk is not hypothetical. The history of planetary science is a history of expectations, overturned by direct observation. Before spacecraft visited Venus, many scientists expected a warm, wet world beneath its clouds. The reality was a surface hot enough to melt, led under an atmosphere of crushing carbon dioxide and sulfuric acid. Before rovers landed on Mars, some models predicted subsurface water accessible from the surface. The reality has proven far more arid and hostile than optimistic projections suggested. Every planet and moon that spacecraft have visited in our own solar system turned out to be different from what telescopes alone predicted, often radically different. There is no reason to expect that exoplanets 4 light-years away will match their spectral portraits any more faithfully. And conditions can change. A planet that was habitable when observed from Earth may not be habitable when the ship arrives centuries later. Stellar flares, volcanic winters, orbital perturbations, atmospheric escape, these processes operate on timescales that overlap with the duration of an interstellar journey. The world the astronomers saw is the world as it existed when the light left it, 4 or 40 years before the ship launched. By the time the ship arrives, the planet has been evolving for centuries beyond the last observation. The crew is travelling toward a photograph, not a place, and the photograph may be obsolete before they are halfway there. The arrival problem closes a circle that the generation ship concept would prefer to leave open. The entire justification for enduring centuries of hardship is that something worthwhile waits at the end. If that something cannot be guaranteed, and it cannot, then the generation ship asks its passengers to accept every risk described so far: radiation, genetic degradation, ecosystem failure, mechanical collapse, social fragmentation, gravitational damage, in exchange for a destination that may turn out to be uninhabitable. The passengers who launched the ship made that bargain voluntarily. Their descendants, born into the mission, had no say, and the planet they arrive at may render the entire sacrifice meaningless. There is a deeper paradox buried in the generation ship concept, and it is the paradox that closes the slow travel trap. Every problem the generation ship faces, radiation exposure, ecosystem failure, mechanical breakdown, social collapse, knowledge loss, gets worse the longer the journey takes. Radiation damage accumulates. Ecosystems drift further from equilibrium. Machines wear further toward failure. Social structures strain under longer confinement. Knowledge degrades across more generations. The slower you travel, the more time each of these failure modes has to operate. This means that the generation ship cannot be rescued by making the journey longer. Slowing down does not reduce risk. It increases every risk simultaneously. A 300-year trip is harder than a 100-year trip in every single dimension. A 3,000-year trip is harder still. And a 30,000-year trip, the timescale that current propulsion technology actually demands, is so far beyond demonstrated human capability that proposing it amounts to speculative fiction. The slow path does not solve the distance problem. It repackages it. It converts the barrier of distance into the barriers of biology, mechanics, psychology, and civilization, and then it forces you to endure all of those barriers simultaneously for a duration that exceeds everything humanity has ever sustained. This is why the slow path fails. Not because it is technically impossible to build a large ship, not because humans cannot survive in space for short periods, but B4, it fails because time does to ships and societies what distance does to communication and resupply. It creates gaps too wide for anything human to bridge. A gap of centuries between launch and arrival, a gap of generations between those who chose the mission and those who must complete it. A gap of time so vast that every system aboard, biological, mechanical, social, and psychological, has more than enough room to fail. And so the mind turns naturally to the alternative. If slow travel collapses under the weight of time, then the obvious answer is to go faster. Compress the journey into years instead of centuries. Eliminate the generation problem entirely by making the trip short enough for a single crew to complete. Accelerate to a significant fraction of the speed of light and cross the interstellar gulf before biology, machinery, and sanity give out. The logic feels irresistible. Speed is the solution. Speed conquers time. Speed shrinks the distance. Speed eliminates every problem that patience creates. But speed has a cost, and the cost is not measured in fuel alone. It is measured in energy so vast that human civilization cannot currently produce it, in collisions so violent that empty space becomes a storm of destruction, in radiation so intense that the ship's own velocity becomes the source of lethal exposure. Speed does not remove the barriers. It trades the barriers of time for the barriers of physics. And physics, at the velocities required for interstellar travel, is far less forgiving than time has ever been. The fast path awaits, and what it reveals is that the universe has not built one wall between humanity and the stars. It has built a corridor where every step forward triggers a new collapse behind. The reasoning feels airtight. If slow travel fails because centuries destroy ships, bodies, and civilizations, then the answer is to stop traveling slowly. Compress the journey. Shorten the timeline. Accelerate to a speed so extreme that the interstellar gulf shrinks from millennia to years or even months. Get there before biology decays, before machines break, before society fragments, before the crew forgets why they left. Speed is the obvious escape from the trap of time. But physics does not offer escapes, it offers trades. And the trade the fast path demands is among the most punishing in all of nature. Speed solves the problem of time by creating problems of energy, impact, radiation, and deceleration so severe that each one, taken individually, might be enough to kill the mission. Taken together, they form a wall that no technology currently proposed, or even seriously theorized, can breach for a crewed spacecraft. The first cost of speed is energy, and the price tag is not large. It is incomprehensible. In everyday life, doubling the speed of a moving object quadruples its kinetic energy. A car traveling at 60 miles per hour carries 4 times the energy of the same car traveling at 30. This is classical physics, the simple relationship taught in introductory courses. It holds beautifully for baseballs, automobiles, and even spacecraft at the modest speeds humanity currently achieves. It stops holding as you approach the speed of light. Special relativity, confirmed by over a century of experimental evidence, describes what actually happens to energy at extreme velocities. As an object accelerates toward the speed of light, its effective mass increases, not its rest mass, not the number of atoms it contains, but the amount of energy required to push it even slightly faster. The closer you get to light speed, the more energy each additional increment of velocity demands. At 90% of light speed, the energy required to accelerate the object further has already grown to more than double what classical physics would predict. At 99%, the energy requirement has climbed by a factor of roughly 7. At 99.9%, the factor exceeds 22. The relationship is not linear. It is not even polynomial. It curves upward toward infinity as velocity approaches light speed, and it never levels off. What does this mean in practical terms? Consider a spacecraft with a total mass of 10,000 kilograms, roughly the mass of a large truck. At 10% the speed of light, this vehicle carries a kinetic energy of approximately 4.5 times 10 to the 18th joules. That is roughly 1,000 megatons of TNT. The largest nuclear device ever detonated, the Soviet Tsar bomber, yielded approximately 50 megatons. To accelerate a single truck-sized spacecraft to 10% of light speed requires roughly 20 times the energy of the most powerful nuclear explosion in human history. And a truck is not a crewed starship. A crewed interstellar vessel with life support, shielding, fuel, and habitat would mass hundreds of thousands of kilograms at minimum. Scale the energy accordingly, and the numbers enter a different realm entirely. And 10% of light speed is modest by interstellar standards. At that velocity, Proxima Centauri is still over 42 years away. If you want a trip time measured in single-digit years rather than decades, you need to push significantly faster. At 50% of light speed, the energy requirement for a 100,000 kilogram crewed vessel climbs to roughly 1.4 times 10 to the 21st joules. At 90%, it reaches approximately 1.2 times 10 to the 22nd joules. These are not numbers that belong on engineering spreadsheets. They belong in astrophysics, in the energy budgets of stars and supernovae, not in the fuel tanks of anything humans might construct. To put the energy wall in perspective, total global energy consumption by all of human civilization in the year 2024 was approximately 5.8 times 10 to the 20th joules. That means accelerating a modestly sized crude vessel to 50% of light speed requires roughly 2.5 years of total energy output from every power plant, every engine, every furnace, and every battery on Earth. To reach 90%, you would need over 20 years of total global energy production poured into a single vehicle. These figures assume perfect conversion of energy into kinetic motion with zero waste, which is physically impossible. This is the energy wall. It does not depend on what propulsion system you use. It does not depend on engineering cleverness or future breakthroughs. It is a consequence of the relationship between mass, velocity, and energy as described by special relativity, which has been confirmed by every particle accelerator experiment ever conducted. No amount of technological progress changes the amount of energy required to accelerate a given mass to a given speed. Technology can change how efficiently you convert fuel into thrust, but it cannot change how much energy the universe demands for a particular velocity. And the energy wall is only the entrance fee. You have not yet built the rocket. In 1897, the Russian physicist Konstantin Tsiolkovsky derived an equation that would haunt every propulsion engineer who followed him. The Tsiolkovsky rocket equation describes the relationship between a rocket's exhaust velocity, the ratio of its fueled mass to its empty mass, and the maximum change in velocity it can achieve. The equation is elegant. Its implications are brutal. A rocket carries its own fuel. As it burns fuel and ejects exhaust to produce thrust, it gets lighter. The lighter it gets, the more efficiently it accelerates. This sounds like a virtuous cycle, and in a limited sense, it is. But the equation reveals that the mass of fuel required grows exponentially with the desired speed. Not linearly, not as a square, exponentially. Doubling the desired velocity does not double the fuel requirement. It squares it, roughly. Tripling the velocity cubes it. Reaching interstellar speeds requires mass ratios so extreme that the numbers leave physical reality behind. For conventional chemical rockets, the exhaust velocity is roughly 3 to 5 kilometers per second. To reach even 1% of the speed of light, approximately 3,000 kilometers per second, using chemical propulsion, the mass ratio required would be so large that the amount of fuel exceeds the mass of the observable universe by many orders of magnitude. This is not an exaggeration. It is a direct calculation from the Tsiolkovsky equation. Chemical rockets cannot reach interstellar speeds. The mathematics forbid it absolutely. Nuclear thermal rockets improve the exhaust velocity to roughly 8 to 9 kilometers per second. The mass ratio drops, but remains absurdly high for interstellar velocities. Ion engines push exhaust velocities to 30 or 50 kilometers per second. Better. Still nowhere near sufficient for a crewed interstellar mission. Theoretical fusion rockets might achieve exhaust velocities of several hundred to perhaps 700 kilometers per second. This brings the mass ratio into a range where interstellar travel becomes mathematically conceivable, but the rocket equation still punishes the attempt ruthlessly. At the optimistic end, around 700 kilometers per second, a 150-ton spacecraft trying to reach 8% of light speed would require a mass ratio so extreme that the initial fuel load would outweigh the payload by a factor of nearly 10 to the 15th. Power. That is a quadrillion kilograms of fuel for every kilogram of ship. At lower fusion exhaust velocities, the number climbs by additional orders of magnitude, rapidly reaching masses that dwarf entire star systems. Published analyses of the rocket equation's interstellar implications confirm that even advanced fusion cannot power large crewed vehicles to star-crossing speeds. Only one theoretical fuel source breaks the rocket equation's tyranny: antimatter. When a particle of matter meets its antiparticle, both annihilate completely, converting nearly 100% of their combined mass into energy. This is roughly 3 orders of magnitude more efficient than nuclear fusion, and roughly 10 orders of magnitude more efficient than chemical combustion. An antimatter-powered rocket could, in principle, achieve mass ratios that make interstellar velocities reachable with a reasonably sized spacecraft. But antimatter exists only in theory as a fuel. In practice, the total amount of antimatter ever produced by humanity across every particle accelerator on Earth over several decades amounts to less than 10 nanograms. CERN, the only facility with a dedicated antimatter production program, reported in 2025 that its latest techniques allow the production of roughly 15,000 antihydrogen atoms in a matter of hours, a breakthrough that its own researchers called science fiction just 10 years earlier. 15,000 atoms weigh roughly 25 times 10 to the negative 21 grams. To fuel even a modest interstellar spacecraft would require grams or kilograms of antimatter. The gap between current production and mission requirements spans more than 20 orders of magnitude. It is the difference between a single raindrop and all the water in the Pacific Ocean. Furthermore, antimatter is extraordinarily difficult to store. It annihilates on contact with any ordinary matter, meaning it must be suspended in perfect vacuum using electromagnetic fields. No storage system capable of holding macroscopic quantities of antimatter for the duration of a mission has ever been built or even convincingly designed. The engineering challenges are not incremental improvements on existing technology. They are unsolved problems in fundamental physics. So the energy wall stands, reinforced by the rocket equation. No existing or near-future propulsion system can accelerate a crewed spacecraft to interstellar velocities without requiring either impossible quantities of fuel or an energy source that humanity cannot produce in usable amounts. The physics is clear. The mathematics is settled. The barrier is not a lack of imagination. It is the relationship between mass, energy, and velocity as the universe has defined it. But suppose, for the sake of exploration, that some future civilization solves the energy problem. Suppose they build a fusion reactor of unimaginable power, or learn to manufacture antimatter in bulk, or develop some entirely novel propulsion system that current physics cannot predict. Suppose they accelerate a crewed vessel to 10 or 20% of the speed of light and send it hurtling toward another star. They have now transformed the interstellar medium from an empty void into a hailstorm of destruction. Space between the stars is not truly empty. It contains approximately 1 hydrogen atom per cubic centimetre on average, along with occasional helium atoms, trace heavier elements, and dust grains. At the speeds humanity currently achieves, this material is irrelevant. Voyager 1 has been ploughing through it for decades, with no measurable effect. At 10 kilometers per second or even 100, the interstellar medium is functionally nothing. At 10% of the speed of light, it becomes something else entirely. A single interstellar dust grain with a mass of 1 milligram, smaller than a grain of sand, smaller even than the width of a human hair, carries a kinetic energy of approximately 450 million joules when it strikes a surface moving at 10% of light speed. For context, a bullet fired from a .357 Magnum handgun delivers roughly 720 joules of energy on impact. The dust grain strikes with the force of over 600,000 bullets arriving simultaneously at a single point. That is not a collision, it is a detonation. The grain and the surface it strikes vaporize instantly. A crater forms. Molten material sprays outward. The impact is equivalent to a small bomb detonating against the hull. Research conducted at Lawrence Livermore National Laboratory, modelling the effects of interstellar dust on relativistic spacecraft, calculated that over a 4 light-year journey at 20% of light speed, cumulative dust impacts could erode, melt, or vaporize more than 0.5 millimeter of a quartz surface across the entire forward-facing area of the vehicle. More recent modelling published in the Astrophysical journal examined the interaction of relativistic spacecraft with the interstellar medium in finer detail. The results confirmed that even for gram-scale probes, dust grain impacts at 20% of light speed modify material structure through melting, and that gas atom bombardment heats the leading surface to significant equilibrium temperatures. At 50% of light speed, the energy of each grain impact scales by roughly an order of magnitude. At that velocity, a 1 milligram grain delivers energy comparable to a large conventional bomb, and grains are not the only hazard. The interstellar medium also contains ice fragments, micropebbles, and debris of unknown composition and size distribution between the scale of micron-sized dust and small asteroids. The size spectrum of material in interstellar space is poorly characterized because detecting objects smaller than a star from light years away is functionally impossible. A ship traveling at half the speed of light for a decade sweeps out a volume of space large enough that encountering an object far more massive than a dust grain becomes statistically plausible. A single impact from a pebble-sized object at that velocity would release energy equivalent to a nuclear weapon. Shielding against these impacts is theoretically possible, but practically devastating to mission design. One proposal suggests a forward-mounted sacrificial shield, a massive plate of expendable material positioned ahead of the ship to absorb impacts. The shield erodes over the journey, and the ship survives behind it, but the shield must be enormously thick to withstand the cumulative energy of billions of hydrogen atom impacts and thousands of dust grain strikes. Its mass adds directly to the fuel budget, which is already strained to breaking by the energy wall. Every kilogram of shielding requires additional fuel to accelerate, which requires additional fuel to accelerate the fuel, which spirals upward through the exponential cruelty of the rocket equation. Another proposal involves an electromagnetic deflector, a powerful magnetic field projected ahead of the ship to ionize incoming particles and sweep them aside. This works in principle for charged particles but fails for neutral atoms, neutral dust grains, and any macroscopic debris. It also requires enormous power to maintain a magnetic field strong enough to deflect particles, arriving at a significant fraction of light speed. The power requirement competes directly with propulsion. But dust is not the only thing the interstellar medium does to a fast-moving ship. The hydrogen atoms themselves become weapons. At rest, a hydrogen atom in interstellar space is harmless. It drifts invisibly, carrying negligible energy. But in the reference frame of a spacecraft moving at a significant fraction of light speed, every hydrogen atom in the path ahead approaches at that same fraction of light speed. The atom's kinetic energy in the ship's frame grows with velocity according to the same relativistic equations that govern the ship's own motion. At 10% of light speed, each hydrogen atom strikes the hull with an energy of roughly 5 mega-electron-volts. That is comparable to the energy of particles used in medical radiation therapy. At 50% of light speed, the energy per atom climbs to nearly 150 mega-electron-volts. At 90%, it enters the giga-electron-volt range, comparable to particles in high-energy accelerator experiments. The forward-facing surface of the ship experiences a continuous bombardment of hydrogen and helium nuclei at energies equivalent to a particle accelerator beam, aimed directly at the hull. This bombardment does not come from a distant source that shielding can simply absorb. It is generated by the ship's own motion. The faster the ship travels, the more energetic the bombardment becomes. The ship is creating its own radiation storm by moving through a medium that would be completely harmless if the ship were stationary. This radiation penetrates conventional shielding. It produces secondary particles through spallation, the same process that makes galactic cosmic ray shielding so difficult. It damages electronics, degrades structural materials, and exposes the crew to doses that grow with the square of velocity. A ship traveling at 50% of light speed experiences a forward-directed radiation flux that would deliver lethal doses to an unshielded crew in a matter of days. The ship's speed, the very thing that was supposed to save the crew from the slow travel problem of cumulative radiation exposure, becomes itself the dominant source of radiation. The interstellar medium at rest is a vacuum so perfect that laboratories on Earth cannot match it. At relativistic speeds, that same vacuum becomes a weapon. The universe does not need to place obstacles in the path between stars. It only needs to scatter a few atoms per cubic centimeter across the void. Speed does the rest. There is another physical constraint that connects the energy wall to the human body, and it governs how quickly a spacecraft can actually reach interstellar speeds, even if the energy problem is solved. Acceleration tolerance. The human body can survive brief bursts of extreme acceleration. Fighter pilots endure 7 to 9 G during aggressive maneuvers, though they require specialized pressure suits and training, and they can sustain those forces for only seconds before risking blackout or injury. Sustained acceleration is a different matter entirely. At 1 G, the acceleration due to Earth's gravity, a person feels exactly as heavy as they feel standing on the ground. This is comfortable, indefinitely survivable, and generally considered the upper limit for sustained acceleration on a crewed interstellar mission. Higher sustained accelerations would require the crew to endure the sensation of weighing significantly more than normal for weeks, months, or years. At 2G, a 70-kilogram person feels as though they weigh 140 kilograms. Every movement becomes exhausting. The cardiovascular system strains under the additional load. Sleep becomes difficult. At 3G and above, prolonged exposure causes tissue damage, impaired circulation, and eventually organ failure. Sustained acceleration above 1G for more than brief periods is not a design choice. It is a medical impossibility for a crewed vessel. At 1G of sustained acceleration, the timeline for reaching interstellar velocities is fixed by physics. It takes approximately 35 days to reach 10% of the speed of light, roughly 200 days, nearly 7 months, to reach 50%, approximately 1 year to reach 77%. These are not negotiable timescales. They are determined by the relationship between acceleration and velocity, and the human body's inability to tolerate higher g-forces without damage. During the entire acceleration phase, the ship's engines must fire continuously. Every second of thrust consumes fuel. Every kilogram of fuel consumed during acceleration is a kilogram that was accelerated along with the ship during the preceding seconds, meaning it already consumed fuel to get that fuel up to speed. The rocket equation punishes long burn times with exponential fuel costs. A 35-day burn to reach 10% of light speed is vastly more expensive in fuel than an instantaneous acceleration to the same velocity would be. Not because the final speed differs, but because the fuel must be carried and accelerated along with the payload for the entire duration. Lowering the acceleration to reduce crew discomfort extends the burn time and increases fuel consumption. Raising the acceleration to save fuel injures the crew. There is no favorable trade in either direction. The human body sets a ceiling on acceleration. The rocket equation penalizes the long burns that ceiling requires. The two constraints squeeze the mission design from opposite sides, and the acceleration phase is also the period of greatest vulnerability to the interstellar medium. During the initial weeks or months of thrust, the ship is accelerating through a velocity range where impacts from dust and gas are becoming increasingly dangerous. But the ship has not yet reached its cruising speed. It is too slow to benefit from the time compression effects of high velocity. It is fast enough for impacts to cause damage. It is burning fuel at enormous rates, and it cannot maneuver to avoid obstacles because any lateral thrust disrupts the acceleration profile and wastes fuel. The deceleration phase compounds every one of these constraints. A 35-day acceleration at 1G means a 35-day deceleration at the destination. 6 months up means 6 months down. The same vulnerability to the interstellar medium that plagued the acceleration phase returns during braking, but now the ship is decelerating nose first into the debris field, rather than accelerating away from a cleared launch corridor, and the ship endured the entire coast phase carrying the dead weight of deceleration fuel that added to the mass during acceleration but served no purpose until arrival. The human body sets a ceiling on acceleration. The rocket equation penalizes the long burns that ceiling requires. The interstellar medium punishes every second spent at intermediate velocities, and every kilogram of shielding, structure, and deceleration fuel feeds back into the mass that must be accelerated in the first place. The acceleration constraint is not a secondary design consideration. It is a structural barrier that interacts with every other barrier in the chain. The links hold, and after the energy has been spent, after the dust has been survived, after the radiation has been endured, one more barrier waits. The ship must stop. Accelerating to interstellar speeds consumes monstrous quantities of energy. Decelerating from those speeds consumes exactly the same amount. A ship that cannot decelerate does not arrive at its destination. It performs a flyby, screaming past the target star at a significant fraction of light speed, with only minutes or hours to collect data before the star system falls behind forever. For a robotic probe, this might be acceptable. For a crewed mission, it is absurd. The crew must slow down, enter orbit, and presumably establish some presence at the destination. That means carrying enough fuel or energy to reverse the entire velocity accumulated during the outbound trip. The deceleration problem effectively doubles the total energy requirement for any crewed interstellar mission. If accelerating to 10% of light speed requires the energy equivalent of a year's global output, decelerating from that speed requires another year's worth. The fuel budget doubles. the mass doubles. The fuel needed to carry the extra fuel doubles again. The rocket equation's exponential penalty applies to both halves of the trip independently, meaning the combined mass ratio for an accelerate and decelerate mission is roughly the square of the mass ratio for acceleration alone. Some proposals attempt to dodge the deceleration problem. A magnetic sail, or mag sail, would use the interstellar medium itself as a braking mechanism, deploying a vast magnetic field to create drag against the thin gas between stars. This concept is theoretically sound, but requires a magnetic field kilometers in diameter and superconducting coils that function after decades of relativistic radiation bombardment. Other proposals suggest using the destination star's light pressure to slow a light sail, but this works only for extremely light probes, not crewed vessels. And behind all of these barriers stands the final one, the one that cannot be engineered around, waited out, or solved by future technology. The speed of light is an absolute physical limit. Special relativity does not merely make faster than light travel difficult, it makes it impossible for any object with mass. As a massive object approaches the speed of light, the energy required to accelerate it further approaches infinity, not a very large number. Not a number that a sufficiently advanced civilization might eventually reach. Infinity. The speed of light is not a speed limit in the sense that highway speed limits are speed limits, a number that can be exceeded with sufficient power and willingness to accept penalties. It is a structural feature of spacetime itself. Mass, energy, and the geometry of the universe conspire to ensure that no material object can reach, let alone exceed, 299,792,458 meters per second. This has been confirmed by every particle accelerator experiment in history. CERN's Large Hadron Collider accelerates protons to more than 99.99999% of the speed of light. At that velocity, each proton carries the kinetic energy of a flying mosquito, not because it is massive, but because it has been accelerated so close to the limit that its effective energy has grown by a factor of roughly 7,000 beyond its rest mass energy. Pushing those protons even slightly faster requires disproportionately more energy. Reaching 100% of light speed would require infinite energy. This is not a theoretical prediction awaiting confirmation. It is an observed fact, measured in laboratories every single day. Even at 99% of light speed, the universe remains staggeringly large. Proxima Centauri would be 4.3 years away. The center of our own galaxy would be over 26,000 years away. The nearest large galaxy, Andromeda, would be over 2.5 million years away. Time dilation at extreme relativistic speeds does compress the journey from the traveler's perspective, meaning a crew traveling at 99% of light speed would experience roughly 1/7 the elapsed time compared to observers on Earth. But they must still accelerate to that speed, survive the interstellar medium at that speed, and decelerate at the destination. Each of those steps encounters every barrier already described, amplified by the extreme velocity. Time dilation is often presented as a gift that relativity offers to interstellar travelers. The faster you travel, the slower time passes aboard the ship relative to clocks on Earth. At 90% of light speed, the crew experiences time at roughly 44% of the normal rate. A journey that takes 10 years from Earth's perspective feels like only 4.5 years aboard the ship. At 99%, the ratio compresses further. The crew ages roughly 1 year for every 7 that pass on Earth. At 99.9%, the compression exceeds 20-1. In principle, a crew travelling fast enough could cross enormous distances within a single subjective lifetime, while centuries or millennia pass in the universe around them. This sounds like a solution. It is actually another barrier, one that severs the mission from the civilization that launched it in ways that communication delay alone cannot. Consider a crewed mission to a star 40 light-years away, travelling at 95% of light speed. From Earth's frame of reference, the journey takes approximately 42 years each way. From the crew's frame, time dilation compresses the trip to roughly 13 years each way. If the crew departs Earth in the year 2200, they arrive at the destination around 2242 by Earth's calendar, but feeling as though only 13 years have passed. They spend a year exploring and depart for home, They arrive back at Earth around 2285 by Earth's calendar. 85 years have passed on Earth. Roughly 27 years have passed for the crew. The crew returns to a world that has experienced nearly a century of history they did not witness. The people who launched the mission are dead. Their children are elderly or dead. The political systems, languages, technologies, and cultural references of 2285 bear almost no resemblance to those of 2200. The crew trained for a mission designed by a civilization that no longer exists in the form they knew it. They return as strangers to a world that has moved on without them. This is not a psychological footnote. It is a structural problem for mission design. Who funds a mission whose results will not return for 85 years? Who trains a crew knowing that every person they love will be dead before the mission is half over? Who maintains the ground infrastructure, the communication arrays, the institutional knowledge, the political will to support a mission across nearly a century of elapsed Earth time? The mission requires continuity of purpose across a span longer than most governments have lasted, and the asymmetry runs deeper than politics. Messages sent from the ship during the journey arrive at Earth time-dilated as well. The crew's transmissions are red-shifted, stretched to longer wavelengths by their velocity. The data rates drop, the information becomes harder to decode, and the content of the messages refers to a mission context that is aging differently than the context on Earth. The crew sends a report in what feels like year 5 of the mission. It arrives at Earth decades after launch. The scientists who designed the instruments described in the report have retired. The software that processes the data format has been superseded 3 times. The institutions that were supposed to receive and analyze the data have reorganized, merged, or dissolved. Time dilation does not eliminate the cost of interstellar travel. It shifts the cost from the travelers to everyone they left behind. The crew ages slowly. The civilization ages at the normal rate. The gap between them grows with every passing year, measured in one frame and felt in both. If the entire purpose of interstellar travel is to extend human civilization's reach, time dilation undermines that purpose by disconnecting the travelers from the civilization they represent. They become temporal exiles, moving through the universe at a different rate than the species they belong to, and time dilation only becomes significant at velocities that trigger every other barrier in the chain. You do not get meaningful time compression below roughly 50% of light speed. At 50%, the dilation factor is only about 13%, barely noticeable. The compression that actually matters for interstellar journey planning, factors of 2 or 5 or 10, requires velocities above 90% of light speed, velocities where dust grains detonate against the hull, where hydrogen atoms become a radiation storm, where the energy budget exceeds the output of entire civilizations, where deceleration doubles every cost. Time dilation is not a loophole in the barrier. It is a feature that becomes available only at speeds where every other barrier is at its most severe. There is no speed at which interstellar travel becomes simple. Slow speeds create time barriers, moderate speeds create energy barriers, high speeds create impact and radiation barriers. Extreme speeds push against the absolute wall of light speed and demand infinite energy to reach it. The corridor between too slow and too fast is vanishingly narrow, and every point along it carries its own lethal combination of problems. This is the architecture of the fast travel trap. Speed does not solve the distance problem, it transforms it. Every increment of velocity purchases a shorter journey at the cost of exponentially greater energy, exponentially more dangerous impacts, exponentially more intense radiation, and the unalterable necessity of carrying enough fuel or energy to stop at the other end. The universe has priced interstellar speed in a currency that scales faster than any engineering budget can follow. And here is the deepest cruelty of the fast path. Every proposed solution to one of these problems worsens another. Add shielding to survive dust impacts, and you increase mass, which increases fuel requirements, which increases energy demands. Increase speed to shorten radiation exposure time, and you increase the energy of each hydrogen atom striking the hull, which increases the radiation dose per second. Carry fuel for deceleration, and you double the mass that must be accelerated in the first place, which doubles the energy requirement for the outbound trip. Build a larger ship to carry more shielding, more fuel, and more redundancy, and you increase the total mass that must be pushed to interstellar velocity, which pushes the energy requirement further toward the impossible. Every solution is a cost. Every cost is a new barrier. Every barrier links back to the others in a closed loop of escalating demands. There is no free variable. There is no parameter that can be adjusted without tightening a constraint somewhere else. The physics does not offer a path through. It offers a chain, and every link is welded to the next. The slow path failed because time destroys everything human. The fast path fails because speed turns everything. The vacuum itself, the atoms of hydrogen drifting harmlessly between the stars, the grains of dust that have floated in the void for millions of years, into instruments of destruction aimed directly at the traveller, and the energy required to reach the speeds where this destruction begins exceeds the output of entire civilizations. Two paths, two failure modes, and they are not independent. They are the two ends of a single spectrum, connected by the distance between stars and governed by the same physical laws. The universe did not build two separate walls. It built one barrier with two faces. Approach slowly, and time devours you. Approach quickly, and physics devours you. The space between these two extremes is the space where interstellar travel must occur, and every point in that space carries its own combination of the same lethal forces. What remains is to look at the chain itself, to survey the proposals that claim to break it, and to ask whether any of them, singly or in combination, can actually sever enough links to open a path. The answer reveals the full shape of the barrier the universe built. Not a gate, not a wall, not a single obstacle that future genius might overcome. A chain of physical constraints, each one reinforced by the others, each one worsened by any attempt to solve its neighbour. The stars are visible, the distances are measured, the destinations are real, and the chain holds. By now the shape of the problem is visible. Distance forces duration. Duration destroys biology and machines. Speed conquers duration but unleashes energy costs, impact hazards, and radiation storms. Energy limits speed. The speed of light caps everything. Each barrier connects to the next in a sequence that no single breakthrough can interrupt, because solving any one link shifts the load onto the others. But perhaps the picture is too abstract. Perhaps the barriers seem like problems that future technology will simply dissolve the way electricity dissolved the problem of darkness, or antibiotics dissolve the problem of infection. So let us walk through the most serious proposals that engineers and physicists have put forward for crossing interstellar space, not to dismiss them, but to see clearly what each one actually solves and what it leaves standing. Fusion propulsion is the nearest term serious candidate. Nuclear fusion, the process that powers the sun, converts hydrogen into helium and releases energy far more efficiently than chemical combustion or nuclear fission. A fusion rocket would heat propellant to extraordinary temperatures and expel it at exhaust velocities of several hundred kilometers per second, perhaps approaching 700 kilometers per second in optimistic designs. This is roughly 100 times better than the best chemical rockets. It brings the rocket equation into a range where interstellar velocities are at least mathematically reachable. But reachable does not mean practical. Even with fusion exhaust velocities, a crewed spacecraft with a mass of a few hundred tons would require fuel masses equivalent to thousands or tens of thousands of times the payload mass to reach even a few percent of light speed. And a few percent of light speed means a journey to Proxima Centauri lasting a century or more. Every generation ship failure mode described earlier returns in full force. Radiation, ecosystem collapse, mechanical degradation, social fragmentation. Fusion propulsion shortens the journey from tens of thousands of years to hundreds of years. It does not shorten it to a human lifetime. The slow travel trap remains open, merely compressed. Furthermore, sustained fusion propulsion at the scale required for interstellar travel has never been demonstrated. No fusion reactor on Earth has yet achieved sustained net energy gain, let alone been miniaturized into a spacecraft engine capable of continuous thrust for years. The engineering gap between current fusion research and a flight-ready interstellar fusion drive spans decades at a minimum, and possibly much longer. Fusion is a real physics phenomenon. Fusion propulsion is still an aspiration. The Bussard ramjet was proposed in 1960 as a way to circumvent the fuel problem entirely. Instead of carrying fuel from launch, the ramjet would scoop hydrogen from the interstellar medium using an enormous magnetic funnel, compress it, and feed it into an onboard fusion reactor. The ship would accelerate continuously, gathering fuel as it traveled, never running out, because the medium itself provided an endless supply. The concept is elegant. The physics is devastating. The interstellar medium is so thin, as established earlier, that collecting enough hydrogen for meaningful thrust would require a magnetic scoop spanning hundreds or thousands of kilometers in diameter. The energy required to maintain such a field is enormous, and the drag produced by interacting with the interstellar medium at high speeds may actually exceed the thrust the collected hydrogen can provide. Multiple analyses have concluded that the Bussard ramjet, as originally conceived, would function as a brake rather than an engine at velocities above a few % of light speed. The medium you are scooping for fuel is the same medium that creates lethal dust impacts and radiation at those velocities. The fuel source and the hazard are the same substance. Antimatter propulsion remains the only theoretical fuel source with sufficient energy density to power a crewed interstellar mission at velocities high enough to avoid the slow travel trap. As discussed earlier, the barrier is not theoretical but practical. Total antimatter production in human history amounts to less than 10 nanograms. CERN's entire antimatter program, the most advanced in the world, produces quantities so vanishingly small that at current rates it would take quadrillions of years of continuous production to accumulate a single gram. The energy required to manufacture antimatter exceeds the energy the antimatter itself contains by a factor of roughly 10 billion. Antimatter propulsion is not an engineering problem, awaiting a clever solution. It is a resource problem of a kind humanity has never faced, requiring a substance that does not naturally exist in our part of the universe, produced by processes that consume far more energy than they yield, stored by methods that do not yet work. Laser sails offered a different approach entirely. Rather than carrying fuel, a spacecraft could be propelled by a beam of light from a powerful laser array. The breakthrough Starshot initiative, announced in 2016 with $100 million in backing and Stephen Hawking's public endorsement, proposed using a ground-based laser array of 100 gigawatts to accelerate gram-scale probes to 20% of the speed of light. At that speed, a tiny probe could reach Alpha Centauri in roughly 20 years and transmit data back to Earth 4 years later. The concept addressed several barriers simultaneously. No fuel on board, no rocket equation, no slow travel timeline, but it introduced new ones just as severe. The laser array would need to produce 100 gigawatts of coherent, focused power, roughly equal to the entire output of every nuclear power plant in the United States combined, directed with a precision of fractions of an arc-second onto a sail 4 meters wide that is accelerating away from Earth at 40,000 times the force of gravity. No existing laser system approaches this capability. The cost reduction required to make the array affordable, roughly a 1,000-fold decrease from current laser prices, would take decades even under aggressive development. And by 2025, the project was effectively dormant. A scientific American investigation revealed that only $4.5 million of the pledged $100 million had been spent. Meetings had ceased. Funding had dried up. Researchers had moved on. The initiative had normalized the idea of interstellar probes as a legitimate scientific goal, but it had not solved any of the fundamental engineering challenges. The sail materials, the laser coherence, the beam tracking, the atmospheric correction, the data return from a gram-scale probe 4 light-years away. Every one of these remained unsolved. Even if breakthrough Starshot had succeeded perfectly, it would have accomplished something narrow and specific. A flyby of another star system by a chip-sized probe carrying a camera. No humans. No deceleration, no orbit, no landing, no return. A postcard from the stars, sent by a machine too small to carry a crew, too fast to stop, and too far away to repair if anything went wrong. This is not interstellar travel in the sense that the dream envisions. It is interstellar observation. The distinction matters, and this is where the chain reveals its most important feature. Every proposal solves some links. None of them solves all the links. Fusion addresses propulsion, but not speed. Antimatter addresses speed, but not production. Laser sails address energy source, but not crew. Generation ships address crew but not time. Each concept breaks one section of the chain only to find that the remaining sections still hold firm. The barriers are not independent problems waiting for independent solutions. They are coupled. They reinforce each other. Solving one redistributes the load across the others, and the total load does not decrease. There is another barrier that receives less attention than energy and speed, but may be equally fundamental: communication. A signal travelling at the speed of light from Proxima Centauri takes 4 years and 3 months to reach Earth. A round-trip message, question and response, takes 8.5 years. This is not a delay that clever engineering can reduce. It is the speed of light applied to the distance between stars. No faster channel of communication exists in known physics. For a robotic probe, this delay is frustrating but manageable. You send instructions, you wait years, you receive data, you send new instructions. The process is slow but functional because the probe does not need real-time guidance. For a crewed mission, the implications are devastating. A crew en route to another star cannot consult mission control. They cannot receive updated navigation data in time to adjust course during critical maneuvers. They cannot request medical advice for an emergency that will be over before the message reaches Earth. They cannot report a system's failure and receive troubleshooting guidance within any useful time frame. If a catastrophic event occurs 3 years into a 5-year journey, Earth will not learn about it until 7 years after the ship launched, and any response will arrive 11 years after launch, 6 years after the crew either solved the problem themselves or died. This is not merely inconvenient, it severs the relationship between the mission and the civilization that launched it. Every space mission in human history has depended on continuous communication with ground support. Apollo relied on real-time telemetry and voice communication with Houston. The Mars rovers received daily command uploads. The International Space Station maintains constant contact with multiple ground stations. Communication is not an accessory to crewed spaceflight. It is a structural pillar. Remove it, and the crew must carry within themselves every skill, every piece of knowledge, every contingency plan that might be needed for the entire journey. They must be not merely astronauts, but an entirely self-sufficient civilization compressed into a vehicle, which leads to the next link. Repair and resupply across interstellar distances is physically impossible in any meaningful sense. The International Space Station, as already noted, cannot survive without regular resupply from Earth, but the specific dependencies reveal how deep the problem runs. Its oxygen generation system requires chemical canisters manufactured on the ground. Its water recycling system uses filters that wear out and must be replaced with Earth-built components. Its attitude control system depends on thrusters consuming fuel delivered from the surface. Every critical function aboard the station traces back to a supply chain that begins on Earth. The station is not self-sufficient. It is an outpost maintained by a continuous lifeline from below. An interstellar spacecraft has no supply line. Once it passes beyond the reach of any conceivable resupply vehicle, which happens within the first few years of flight at interstellar speeds, every resource aboard is the total resource that will ever be available. If a critical component fails and no spare exists, the function it served stops permanently. If a medical emergency requires a drug that was not stocked, the patient receives no treatment. If food production falls short because a crop fails or a recycling system degrades, the calorie deficit cannot be corrected from outside. This is not a problem of foresight. It is a problem of completeness. No finite inventory can anticipate every possible failure mode across decades or centuries of operation in an environment that has never been inhabited. Engineers can model expected failures. They cannot model unexpected ones. And in a journey lasting decades, the unexpected is statistically guaranteed to occur. The requirement for total self-sufficiency also means the ship must carry manufacturing capability. Not just spare parts, but the tools to make spare parts. Not just raw materials, but the industrial processes to convert raw materials into functional components. Machine shops, smelting facilities, chemical synthesis equipment, semiconductor fabrication, if electronics need replacement. Each of these capabilities adds mass, complexity, crew training requirements, and failure points. The ship must be not a vehicle but a factory, a hospital, a farm, a school, and a government, all enclosed in a structure hurtling through vacuum, with no possibility of external assistance. No human institution has ever achieved this kind of total self-sufficiency. Not island civilizations, not submarine crews, not Antarctic research stations, not space stations. Not. Every isolated human community in history has depended on trade, resupply, or access to natural resources from a surrounding environment. An interstellar spacecraft has no surrounding environment. It carries everything or it carries nothing. Now step back. Look at the full chain. Distance forces the journey to last years at minimum, centuries or millennia at realistic speeds. Duration degrades biological systems through radiation exposure and genetic drift. Duration degrades mechanical systems through wear, fatigue, and the absence of external repair. Duration degrades social systems through isolation, confinement, and generational drift. Speed reduces duration but demands energy that exceeds civilizational output. Speed turns the interstellar medium into a barrage of high-velocity projectiles. Speed turns drifting hydrogen atoms into a forward-directed radiation storm. The speed of light imposes an absolute ceiling that no technology can breach. Deceleration doubles the energy cost. Communication delay eliminates ground support. Distance eliminates resupply and rescue. Self-sufficiency requirements demand industrial capability that no enclosed system has ever demonstrated. Each barrier links to the next. Each solution to one barrier increases the cost imposed by another. The chain does not have a weakest link that, once broken, causes the whole structure to fall. It is a chain in which every link is load-bearing, and every link transfers force to its neighbours. Sever one, and the load shifts. The remaining links hold. The chain tightens. This is what makes interstellar travel physically impossible for human beings in any currently meaningful sense. Not a single overwhelming obstacle. Not a dramatic prohibition written into the laws of physics. Not a locked gate with a key hidden somewhere in future science. A chain of constraints, each one rooted in fundamental physics, each one reinforced by the others, collectively producing a barrier that no single technology can overcome because the barrier is not singular. It is systemic. And here, before the end, something must be said clearly. Because this claim that interstellar travel is physically impossible is easily misunderstood, and misunderstanding it distorts everything. Physics does not forbid objects from entering interstellar space. Voyager 1 and Voyager 2 are in interstellar space right now. They are functioning, more or less, transmitting data back to Earth, crossing a void that was once purely theoretical. Tiny robotic probes may follow within decades, accelerated by lasers or propelled by advanced engines, carrying instruments that can photograph another star system and send the images home. These missions are physically possible. They may be engineering achievements within the reach of current or near-future civilization. What the barriers prevent is not exploration. It is habitation. It is the transfer of living human beings from one stellar system to another, alive, functional, and capable of doing something meaningful upon arrival. That specific goal, the dream of human interstellar travel, runs into the full weight of the chain. Not because any one barrier is insurmountable in isolation, but because the barriers never present themselves in isolation. They arrive together, coupled, mutually reinforcing, and they demand simultaneous solutions to problems that span physics, biology, engineering, psychology, sociology, and logistics across timescales that exceed all human experience. This is not pessimism. It is not a declaration that science will never advance. It is not a claim that the laws of physics as currently understood represent the final word on what the universe permits. It is a recognition that the barriers between stars are not gaps waiting for bridges. They are the structural features of a universe built on specific physical constants, specific relationships between mass and energy, specific limits on the speed of information, specific vulnerabilities in biological organisms, and specific rates at which entropy degrades ordered systems. These features are not design flaws. They are not obstacles placed by a hostile cosmos to test human resolve. They are the architecture of reality. The universe was not built for crossings at this scale. It was built for stars to burn in isolation, separated by distances that dwarf anything biology has ever needed to traverse. Understanding this honestly does not diminish the dream. It clarifies it. The desire to reach another star is among the most beautiful impulses the human mind has ever produced. It emerges from the same capacity for wonder that drove the Polynesians across the Pacific and the Apollo astronauts to the moon. But wonder and capability are not the same thing. The Pacific was crossable because wind and water and human endurance operated on scales that matched the distance. The moon was reachable because chemical rockets and 3-day transit times operated on scales that matched the challenge. The stars do not match. The scales are wrong. The distances are too large. The energies too extreme, the timescales too long, and the medium too hostile for the biological and mechanical systems that human beings depend on. And perhaps that is not a tragedy. Perhaps it is simply what the universe is, a place of staggering beauty observed from positions of profound confinement. We can see the stars, we can study their light, we can identify their planets and analyze their atmospheres and calculate whether life might exist on their surfaces. We can send tiny machines into the interstellar medium and listen for their whispered signals across light days and eventually light years of distance. We can know the cosmos with extraordinary precision and intimacy from exactly where we are. What we almost certainly cannot do, within any timescale that maps onto human civilization as we know it, is walk there. Voyager 1 is still out there. Right now, as these words reach you, it is drifting through the interstellar medium at 17 kilometers per second. Its radio signal, weakened to a whisper after traveling for nearly a full light day, still reaches the deep space network antennas on Earth. Engineers at the Jet Propulsion Laboratory still send commands and receive responses, though each exchange now takes nearly 48 hours round trip. Most of its instruments are silent. Its power source, a lump of decaying plutonium, generates less electricity than 3 household light bulbs. Within a few years, even that will fall below the threshold needed to run anything at all. Voyager 1 will go quiet. It will continue traveling. It will not stop. Nothing in interstellar space will slow it down appreciably for billions of years. In approximately 40,000 years, Voyager 1 will pass within about 1.6 light-years of a star called Gliese 445 in the constellation Camelopardalis. It will not stop there. It will not enter orbit. It will drift past, unnoticed, carrying a golden record encoded with greetings in 55 languages, music from Bach to Chuck Berry, the sound of a human heartbeat, and the brain waves of a woman thinking about love and the history of Earth. No one will play it. The distance is too vast. The silence is too deep. The record will outlast the civilization that made it by an interval that dwarfs the entire span of human history. But the record exists. And so does the dream. And so does the knowledge, hard-won and precise, of exactly why the stars remain beyond our reach. The universe did not build one wall between humanity and the stars. It built a chain, distance, time, energy, speed, radiation, dust, biology, mechanics, isolation, communication, each link forged from fundamental physics, each link welded to the next. No single breakthrough severs the chain because no single link bears the load alone. The weight is distributed. The structure holds. This is not a locked gate with a key hidden in the future. It is the shape of the universe itself, expressed in the distances between stars and the constants that govern mass, energy, and light. The stars burn. The void stretches between them, and we, on our small world, look up with a longing that physics cannot answer and a clarity that perhaps only physics can provide. The barrier the universe built is not cruelty, it is architecture. And understanding the architecture, honestly and completely, may be the closest we ever come to crossing it.